Okay, now let's talk about how to use the chi-squared table. It's pretty much like using the t-table. So in terms of what you can do with it, it's the same sort of thing. If you want like the probability chi-squared is less than 10 or something, there is no way to get this with the table. All you can do is if you know the probability you want, so say 0.95 or one of those values like that, 0.9, 0.99, and you know your degrees of freedom, then you can get chi-squared. That's all you can really use the chi-squared table for, just like it was with the t-table. So let's pull up the table and look at it. So let me zoom in. And scoot over. So here's the chi-squared table. So it's basically just like the t-table. The alpha values it gives here are for a right tail test. If you have a two tail test, then you would split these in half, just like it tells you to. And we'll see that. We're going to do a two tail test here in a second. So here's the value of alpha you're interested in. Here's the degrees of freedom. And this gives you your value of chi-squared. Alright, so let's actually do a hypothesis test, because that's what you're going to be using this for anyway. So let's say the standard deviation is supposed to be 4 days hospital stay after a car wreck. And we have to take 15 patients and we compute their standard deviation, and it winds up only being 2.7 days. Then the question is, well, is this standard deviation correct, or did we just get a bad batch? Well, I guess I should give you an alpha. Let's say alpha is let's go stringent this time, 0.01. Okay. Well, again, for figuring out our critical value of chi-squared, we don't need the standard deviation or the population standard deviation. All we need to know is this number of patients, because that gives us degrees of freedom. We need to know this alpha. And we need to know, is this left-tailed, right-tailed, or two-tailed? Well, the claim is that sigma equals 4. So that means our alternative is going to be sigma is not equal to 4. So the picture is this is going to be our rejection region like this, because we want anything bigger or anything smaller to be rejected because of this not equals. Alright. Well, if alpha is 0.01, that's the area of the rejection region. So if this area is 0.01, that means each piece of it here is 0.005. Which means these two values we're going to look up are the ones for 0.005 here. And actually I did that the wrong way around. I think this table is right instead of left. So this one would be 0.005. It really doesn't matter if you do it backwards, you'll still get the same thing. And this one is 0.995. So we're going to look up these two alphas on the table with 14 degrees of freedom, and that's going to give us our chi-squareds. Alright, let's grab this table. So alpha 14 degrees of freedom for 0.995. This is where chi is 4.075. So for this one, let me change colors. Everything's the same. So here, chi squared is 4.075. And then for our alpha is 0.005 and 14 degrees of freedom. That's the right one. 31.31.9. So this is chi-squared is 31.319. So these are our two critical values for chi-squared. So now we're just going to figure out our test statistic and see, hey, is this somewhere in the middle, in which case we don't reject, or is it in one of our two rejection regions? And standardized test statistic is chi-squared is n minus 1 s squared over sigma squared. So our n minus 1, whoa, that was weird. So our n minus 1 is 14. S squared, well, they gave us standard deviation. So if they'd given us variance, we wouldn't actually have to square it because the variance is already squared. Over 4 squared. This is what? 14 times 2.7 squared divided by 4 squared is 6.37. So we're somewhere around here. So this one we will fail to reject because we're not in the rejection region. It's like we thought, well, this 2.7 seemed low, but it wasn't low enough. We'd have to get from the 6.37 down, somewhere down below this 4.07 if we wanted to actually reject this. All right, well, that's how you use the chi-squared table.